This is the General Motors Proving Ground in Milford, Michigan. It is the automobile equivalent of boot camp, a place to see whether prototype vehicles can survive a grueling series of tests. Everything is examined. Road handling, crash worthiness, and a vehicle's handling under adverse conditions. In addition, there are tests of engine performance, mileage, and the amount of pollutants a vehicle gives off. Testing prototype cars for harmful emissions is serious business. Clean air laws put strict limits on the amount of pollutants a car can emit. The Environmental Protection Agency randomly tests cars coming off the production line, and if they exceed the limits, the cars can't be sold.
The ultimate consequence for not meeting the standards is you're not permitted to sell the vehicle. That's catastrophic.
So GM needs complete assurance that a prototype engine will actually perform within legal limits when it's mass-produced. A number of prototypes are built, and the pollutants they emit are measured under controlled conditions. The measured emissions tend to be normally distributed. Some engines are low, some are high, and most fall somewhere in between. In this unit, we're going to see how GM uses normal distributions to predict the performance of an entire line of new automobiles. We'll see that when we work with normal distributions, we can standardize our measurements, which means to translate them into units of standard deviation. We'll see that we represent standardized measurements with the standard normal curve, which has a mean of 0 and a standard deviation of 1. And we'll learn to use the standard normal table to find the percentage of observations lying below a specific point on the standard normal curve. Let's say that GM tests a number of prototype engines for a class of pollutants called nitrogen oxides, or NOx for short. The testing engineers know that not all engines emit exactly the same amount of NOx. There's variation. That variation from engine to engine follows a normal curve like this. The tests of prototype engines allow the engineers to estimate quite closely the mean, mu, and standard deviation, sigma, for this curve. For this particular engine model, the mean is 0.78 grams of NOx emitted per mile, and the standard deviation is 0.5 grams per mile. Now, areas under this curve show us the percentage of observations falling in a given range. We're now going to see how to find these percentages exactly by standardizing. This means describing the measurements in terms of standard deviations away from the mean. We standardize our measurements by taking each value x, subtracting the mean, mu, and dividing by the standard deviation, sigma. The result is the standardized measurement, which we call z. Now let's use this recipe on our distribution of NOx levels. One particular engine emits 1.06 grams of NOx per mile. We can immediately see that this is higher than the mean. But how much higher? We can tell if we standardize the measurement. X is our measurement, so it's 1.06. Then we subtract the mean, 0.78, and divide by the standard deviation, 0.5. We get z equals 0.56. This is the standardized measurement of the emission test, and it means the measurement is 0.56 standard deviations above the mean. If we standardized all of the individual measurements like this, we would get a collection of z values. The distribution of these z values will still be normal, but standardizing produces a special normal distribution, the standard normal curve. Here the mean is set at 0, with a standard deviation of 1. Here's 1 standard deviation on either side of the mean. Here's 2, and here's 3. If an original observation falls below the mean, its z is negative, and if it's above the mean, the z is positive. We can use the standard normal curve to tell us where specific observations lie in relation to the rest of a distribution. For instance, let's take a look at our engine with a standardized NOx level of 0.56. That's here on the standard normal curve. What percentage of all engines had NOx emissions lower than this? To find out, we can use a table of percentages, called a standard normal table, or a z-table. Here is a portion of the table. First, we enter the table at our given z, which is 0.56. The column at the left gives the first part of the z number, the tenth portion. The row across the top is used for the second decimal place of the z number. Our z was 0.56, so first we look for 0.5 in the vertical column. Then look for 0.06 in the top row. The two intersect on a number that corresponds to the area under the curve below that z number. Here, that's 0.7123. We can read this as a percent by shifting the decimal point 2 places to the right. So 0.7123 is the same as 71.23%, which we can round to 71%. Now we know that about 71% of the observations in the distribution lie at or below a z-value of 0.56. Let's try another one. What's the percentage of observations falling below a measurement with a z-score of negative 1.52? Now remember, the negative z-score means the score falls below the mean. Using the table again, we look for negative 1.5 in the column on the left and 0.02 in the top row. The corresponding number is 0.0643, or about 6%. So only 6% of observations fall below this observation. Now we've learned that we can standardize measurements using our z formula, and that we use the standard normal curve to represent our standardized values, or z values. Let's see how these techniques are used by GM. We said that GM tested a number of prototype engines in an effort to tell whether the design would pass environmental regulations. The tests measure many types of pollutants, but we'll look at only one, NOx. The legal limit for NOx emissions is 1 gram per mile, but not every vehicle has to meet this standard. Since emissions vary from car to car, the law says that up to 40% of manufactured cars can exceed the limit. So the question is, how can GM use the emissions data from the prototypes to tell whether the mass-produced cars will pass? This is where GM statistician Tom Lorenzen enters the process.
We assume that the NOx emissions are normally distributed and test a few prototypes in order to calculate a mean and standard deviation. Based on the mean and standard deviation and the bell-shaped curve, we can calculate the probabilities of exceeding the standards, and would like that to be as small as possible. Even though EPA allows 40%, the design standards are typically much lower than that. We'll shoot for 10 to 20% just to be sure.
Here again is our normal curve of NOx emissions from prototype engines with a mean of 0.78 and a standard deviation of 0.5. We want to know what percentage of all such engines have pollution levels greater than 1 gram per mile, the limit set by law. On this scale, the 1 gram point is here, and therefore the area we're interested in is here. First, we need to standardize the limit 1. Using our z recipe, we substitute 1 for x, then subtract the mean, that's 0.78, and divide by 0.5. Our z value is 0.44. The original 1 gram per mile limit, when standardized, becomes 0.44. And this means the limit is 0.44 standard deviations above the mean on the standard normal curve. Now we can use the table to tell us what percentage of observations lie below this z value. The corresponding number in the table is 0.6700, or 67%. What we wanted to know, of course, wasn't how many were below the limit, but how many exceeded the limit. Since the total area under any density curve is 1 or 100%, we can just subtract 67% from 100% to find our answer. It's 33%. So GM has found that based on their testing of prototype engines, about 33% of engines manufactured from the prototype could be expected to exceed the legal limit. Now that's not bad, since the law allows 40% of the cars to exceed the limit. But 33% is fairly close to the limit. In fact, even though it passes, 33% isn't good enough for GM. The company doesn't want to gamble millions of dollars on an engine design that comes so close to the limit. This design would be sent back to the drawing boards, which these days are electronic.
If too many fail at the prototype stage, then it calls for a redesigning of the engine. Design engineers then look at the problem and determine methods that will keep the car running well, keep the fuel economy high, yet decrease emissions.
As we've just seen, we can use the standard normal curve and the standard normal table to find the percentage of observations falling above or below any point on the curve. But we can also work the other way around, finding a particular standardized value if we know a specific percentage. To see how this works, let's look at a problem the Army faced not long ago.
I'm a soldier, to my job, always to my best.
Let's say the Army wants to manufacture a new type of helmet, but they don't want to bother making lots of helmets for soldiers with unusually big heads. It's cheaper for the Army to custom make helmets for such people. The Army decided not to make helmets in advance for the 5% of soldiers with the biggest heads. The question is, what head measurement corresponds to that percentage? In other words, this time we know the percentage, 5%, and we want to find the head size to which it corresponds. In this case, the head size is the measurement below which 95% of the soldiers fall. Well, our procedure here is exactly the reverse of the process we use to find a percentage. This time we start with the table, get a z-value, then go from z to the original scale. Since the table gives the area below any level, we search the body of the table for the entry closest to 95%. That's 0.95. And here it is, 0.9505. Using the table in reverse gives us a z of 1.65. Now remember that this is the standardized measurement. It tells us how far from the mean this measurement is in terms of standard deviations. But now we need to unstandardize to get back to the units of the original measurements, in this case, head sizes in inches. So we continue to work in the opposite way. We'll use our z formula again. We just found z, and that's 1.65. The mean of the head sizes measured by the Army was 22.8 inches, so mu is 22.8. And the standard deviation is 1.1, so sigma is 1.1. Now we can solve for x using the rules of algebra. First, we multiply both sides by 1.1 to clear the fraction. Then we add 22.8 to both sides to isolate our variable, x. And our answer is 24.6 inches. And this means that 95% of the soldiers in the Army can be expected to have heads 24.6 inches around or smaller. And so the Army can now tell its manufacturer to mass-produce helmets up to 24.6 inches, but no larger. Soldiers with heads larger than this will get custom-made helmets, which saves the Army money and prevents a few soldiers from getting sore heads because of ill-fitting helmets.
What the Army done to me? Took away my blue jeans. Took away my blue jeans. And now I'm wearing Army green.
In this unit, we've learned some valuable skills for analyzing data when their distribution is close to normal. We've seen that we can convert any normally distributed data into standardized units, which are units of standard deviation. We've learned that our standardized values can be represented by the standard normal curve, with a mean of 0 and a standard deviation of 1. And we've learned to use a table of areas under the curve to find a percentage given a specific z-value, or to find a z-value given a specific percentage.